Hi, my name is Giovanni Geraci. This video is the second one of a series of lectures for the course Signals and Systems 2 at Universitat Pompeu Fabra in Barcelona. If you haven't watched the first video yet, I recommend starting from that one. And if you have any questions, feel free to get in touch via email. You can also check my webpage for more information about me. As we said in the previous class, signals and systems arise in a variety of disciplines. In this class, we will continue developing a mathematical framework to represent and work with continuous time signals. Today, we will introduce the notion of continuous time systems, which operate on continuous time signals. A system can be viewed as an interconnection of components, devices, or subsystems. So you can imagine a telecommunication system, a car, a chemical plant, etc. They are all processes where an input signal is transformed into an output signal, which is a response. For example, speakers take an audio signal as an input and reproduce it as an output. We will focus on continuous time systems, which take continuous time inputs and produce continuous time outputs. So you can picture a system as a box like the one you can see on the top right of this slide, where there's an input x of t, it's a continuous time input signal, and there's an output y of t, which is also continuous time. Okay, systems can also be interconnected. Okay, actually many real systems are built as interconnections of several subsystems or several components. And there are different ways we can interconnect systems. Series, for example, or cascade, parallel, feedback, which we'll see more in detail later, and also combinations of all of the above. Right, so what's an example of a series interconnection? A radio receiver followed by an amplifier. What's an example of a parallel interconnection? An audio system with several microphones feeding into a single amplifier and speaker. So as you can see in the middle picture, there's a series interconnection where a certain input goes into system 1 and the output of system 1 is fed into system 2 as an input. And system 2 in turn produces an output. For a parallel interconnection, which is the bottom right figure, we have an input which is common to both system 1 and system 2. And then the two outputs of these two systems are added up and they produce an output. So in addition to series or parallel interconnections, we can combine those to obtain a more complicated interconnection. For example, in the figure on top, you see a series parallel interconnection. Certain input goes to a cascade of system 1 and system 2 and also to a system 3. And the output of these two are added up and they are fed into a system 4, which then produces an output for the overall system. But another important type of interconnection is a feedback interconnection, where the output of a first system is the input of a second system, and the output of the second system is fed back and added to the external input of the first system. You see this in the bottom figure. Feedback systems are actually very common. Imagine the cruise control of a car where the fuel flow is the input and the car speed is the output, and such speed is fed back such that the fuel flow is adjusted to keep the desired speed. So what happens is that less fuel is let pass if the speed is too high and more fuel is accepted in if the speed is too low. We will now introduce and discuss several basic properties of continuous time systems. We'll start with linearity. So a linear system is one that possesses the property of superposition. So the response to a linear combination of inputs is the linear combination of the respective responses. So let's start by describing it mathematically. So let y1 of t and y2 of t be the responses to x1 of t and x2 of t respectively. Okay, so a system is linear if the response to the sum x1 of t plus x2 of t is the sum of the responses y1 of t plus y2 of t, and also the response to a x1 of t, meaning x1 of t multiplied by a constant, is a y1 of t, meaning the response to x1 multiplied by the same constant for any complex number a. So combining those two properties, we have more in general the property of superposition, which states that ax1 plus bx2 produces as an output ay1 plus by2 for any two complex constants a and b. We can also note that a zero input produces a zero output for a linear system. Another important property is time invariance, which means that the behavior of a system is fixed over time. So a time shift in the input results in an identical time shift in the output. So if you give x to a system and the system responds with y, when you give x of t minus t0, the system must respond with y of t minus t0. Well, in other words, a system is time invariant if running the same experiment over the system, which means applying the same input, produces the same output today, tomorrow, always, anytime. Okay? So imagine a car where the acceleration you apply produces a certain speed, irrespective of the day you drive the car. So this car is a time invariant system. However, if one day you load the car with heavy suitcases, for example, then the response to the same acceleration would be a lower speed, corresponding to a system that this time is not time invariant. So we will denote as LTI, linear time invariant, a system that is both linear and time invariant. And our focus in this course will mostly be on the analysis of LTI systems, because many real systems possess these properties. So linearity and time invariance, as we said, are two properties that play a fundamental role in signals and systems analysis. As I already said, many real systems possess these two properties, and those that do can actually be analyzed in detail through some tools that we will study in this course. In order to study linear and time invariant systems, let's start by representing a signal, x of t, in terms of impulses through an approximation. So look at the figure. Our signal is represented by a solid line, okay, and we are making what looks like a staircase approximation. So we are approximating our signal with a sum of scaled and shifted versions of delta delta of t, which, if you recall from the previous class, is an impulse that has duration delta and amplitude 1 over delta. We can see the same thing in mathematical formulas. So let's look at the formula at the top of this slide. X hat of t, which denotes the approximation of x of t, the hat denotes an approximation, can be expressed as a sum. A sum of what? Well, a sum, as we said, of impulses. Delta delta of t minus k delta are the impulses, and as you change the value of k, the impulse is located at a different position in time. So when k is 0, you have delta delta of t, which is between 0 and delta. When k is 1, you have delta delta of t minus delta, which is between delta and 2 delta, and so on and so forth, okay? Then the amplitude of this is multiplied by x of k delta, which is the value of the signal x which we want to approximate at that point, at point k delta. And it's further multiplied by a delta simply because we define delta delta as having an amplitude 1 over delta. So this delta basically compensates for that value to normalize to unity. In this sum, for each time, only one term is non-zero. So as we already said, x of t, the approximation, is a sum of scaled and shifted versions of delta delta of t. So sum of scaled and shifted versions of these impulses. So if we're looking for the response of a linear system to x hat, we can call this response y hat. Well, because of linearity, this response y hat will have to be the superposition of the responses to scaled and shifted versions of delta delta of t because of linearity. We can say the same thing in formulas. So let's say that h hat k delta of t is the response to one of these impulses. It's the response to delta delta of t minus k delta. Okay. Then for linearity, we can construct the output y hat of t as the sum of the same coefficients x of k delta and also another delta that multiplies times h hat k delta of t. So we can construct the response y hat as a linear combination of the responses to each of these impulses. And the responses to each of these impulses are h hat k delta of t. Let's see the same thing with images to facilitate understanding. So to the left, we have been representing some of these different impulses that we use to approximate our signal. So if you recall, I said that for different values of k, the impulse is positioned at a different point in time. So the first one you see is positioned at 0, and it's for k equals 0. Then below you have one position at delta, that's for k equal 1. And for a general k, the impulse will be positioned at k delta, okay? And it will have a duration delta. Then each one of these has a corresponding output. Okay, so if you apply each one of these to the system that we're considering, produces respectively an output. So the first one will produce an output that is x of 0, h hat 0 of t, delta, right? And so on and so forth. So here, what we have to understand is that we have decomposed our signal into different impulses. Each impulse produces an output. So the overall signal will produce an output that is the linear combination of such individual outputs. Let's see that in another figure. So here, again, on the top, we see a representation of the original signal, x of t, and the approximation, x hat of t, which is a staircase. It's a combination of impulses, okay? So x hat, the approximation, will have some approximated response y hat, which we had defined in a previous slide. Then x of t, the actual original signal, will have a response y of t. So x hat is an approximation of x, and y hat is an approximation of y, the real response. So we can see the same thing in formulas now. How do we get from x hat to x, and therefore how do we get from y hat to y? So how do we make the approximation better and better? Well, we need to make that staircase finer and finer. We need to choose delta smaller and smaller. So let's do that. So as delta goes to 0, x hat of t, the approximation, converges to the actual signal x of t. And correspondingly, its response, y of t, converges to y hat of t converges to y of t, which is the real output. So let's see this in formulas. All we have to do is a procedure of limit. So we evaluate y hat of t, which we have already defined previously, for a delta that goes to 0. for a delta that becomes smaller and smaller. So the sum becomes an integral and the variables become continuous. So the result of this is an integral between minus infinity and infinity of x of tau, tau is a mute variable, h of t minus tau d tau. The same thing can be written with this symbol, which is an asterisk or a star. So it can be written as x star h. This operation is called a convolution. So this is what we call the convolution integral. It plays a very important role because given an input of a system and given h of t, which we will define, it tells us what the output is going to be. So in this formula, and in this integral in particular, h of t minus tau is the response to an impulse, delta of t minus tau. So if you remember, hk delta was defined as the response to an impulse of duration delta. Now we're making delta smaller and smaller. Delta is going to 0, okay? So the impulse tends to a delta, to a Dirac delta, to the ideal impulse. And the corresponding response, hk delta, tends to h of t, continuous. So this h of t, in summary, is what we call the impulse response. What is it? Well, as the name says, it's the response to an impulse. So it's what the system would give us as an output if we give delta of t as an input. The important point here is that a linear and time invariant system is completely characterized by h of t, meaning it's completely characterized by its impulse response. So let's have some simple examples. The first example is a time shift system. So it's a system that has as an impulse response delta of t minus t0. So what happens when we give an input x of t? To calculate the output, we do the convolution. So we calculate the convolution between x of t and h of t. So we calculate x of t convolution delta of t minus t0. If we just apply the formula, if we just apply the convolution integral, well, we have x of tau delta t minus tau minus t0 d tau integrated. And this integral is equivalent to x of t minus t0, right? So the output of the system is equivalent to the input, but with a time shift t0, right? So we have completely characterized our system just by saying that h of t is delta of t minus t0. Another simple example that we can give is a system that is an integrator. So a system that does the integral of the input, whatever the input is. Such system is characterized again by h of t, the impulse response, and in this case the impulse response is u of t minus t0, is the Heaviside function. Let's see what happens. So we give an input x of t, the output will be again the convolution of x of t with h of t, which in this case is u of t minus t0. So we feed everything into an integral, we calculate the integral according to the definition of convolution, and we obtain that the output is the integral between minus infinity and t minus t0 of x of tau d tau. So it's actually the integral function of the input. Let us see now some important properties of linear time invariant systems. These can be useful in many cases, for example, when we want to calculate convolutions or when we want to analyze interconnection of systems. It can make our life much easier. So a basic property of convolution is that it is a commutative operation. It means that the roles of x of t and h of t can be exchanged. So if we want to see this in formulas, It's quite simple. H convolution x convolution h is the same as h convolution x, and it's the integral that we have previously defined. What implications does this have? Well, a system with input x of t and impulse response h of t will produce the same output as a system that has input h of t and impulse response x of t. So again, the roles of x and h can be exchanged. Another basic property of convolution is the distributive property. So convolution distributes over addition. This has a useful interpretation. So consider two LTI systems in parallel, as in the figure, with identical inputs and their outputs being added. The equivalent system has h1 of t plus h2 of t as the impulse response. Thus, a parallel combination of LTI systems can be replaced by a single LTI system whose impulse response is the sum of the individual impulse responses in the parallel combination. Yet another useful property of convolution is that it is associative. So this means that the order in which we perform a convolution doesn't matter. As a consequence, the impulse response of a cascade of two LTI systems, like in the figure, will be the convolution of the two respective impulse responses, and the order in which they are cascaded doesn't matter as far as the overall system impulse response is concerned. So as you can see in the figure, you have the first system and then in cascade the second system. Equivalently, you can have one system that has as an impulse response the convolution of the two, or you can have a cascade of two where the position of the systems has been swapped. And the output is the same in all these cases. What about memory? We can say that a system is memoryless if its output at any time depends only on the value of the input at the same time. So there is no memory of the past or of the future. So for linear time-invariant systems, this is equivalent to having an impulse response that is zero everywhere except at the origin. So h of t has to be zero for every t that is non-zero. So what type of systems meet this requirement? Well, a simple system like the one that gives you an output y equal to k times the input. Okay, this system will have an impulse response that is simply k times delta of t. This system would be memoryless. What about invertibility? So an inverse system exists that, when connected in series with the original system, produces an output equal to the input of the first system. So that's the definition of invertibility. So let's explain it more in detail. Imagine you have a system h of t. Then if there's an inverse system h1 of t, then the convolution of h and h1 is equal to delta of t, which is a unitary system. It's a system that gives as output the same as the input. Okay. Well, let's look at the figure. On top, we see that we feed x to a system h, and then we feed the output to h1, and the last output is h, meaning that the second system, h1, has inverted whatever the first system had done. And again, this means that the equivalent system, which is the convolution of the two, has as an impulse response delta of t. Let's see an example to perhaps try to clarify this. Let's take a time shift. So it's a system that has as an impulse response h of t delta of t minus t0. So as we already saw, depending on whether t0 is positive or negative, this can be a delay or an anticipation, right? So the output y of t will be x of t convolution delta of t minus t0. Okay, and what is this? This is x of t minus t0. So it's just the input delayed or anticipated, so time shifted. What if we want to invert it? To invert it, we need to use a system that has impulse response h1 of t equal to delta of t plus t0. This is going to invert whatever delay or anticipation the first system introduced. So we get that h of t convolution h1 of t is equal to delta of t. Another very important property is causality. A system is causal when the output depends only on the present and past values of the input. So for an LTI system, this means that the impulse response h of t has to be 0 for any negative times. So for example, take a time shift that is the same one as we just saw. The impulse response h of t is delta of t minus t0. This is causal if t0 is positive, because it corresponds to a delay. If t0 were negative, it would be an anticipation, and therefore the output would depend also on the values of the future of the input. So the impulse response of a causal LTI system must be 0 before the impulse occurs, which is consistent with the intuitive concept of causality. So more generally, causality is equivalent to the condition of initial rest of a system, meaning if the input to a causal system is 0 up to some point in time, then the output must also be 0 up to that time. Let's conclude with another very important property of a system, which is stability. So a system is stable if every bounded input produces a bounded output, right? And we can try to derive conditions for which this holds. So if we have a bounded input, then the input x of t in magnitude will be bounded, as we just said, by a certain number b, okay? Then what about the output, y of t? What do we need for the output to be bounded, given that the input is bounded? Well, we can just calculate the output with the definition of convolution that we learned today. So y of t is the integral between minus infinity and infinity of h of tau x of t minus tau d tau, which is the convolution integral between x and h, or h and x. It's the same because of the commutative property. This will be taken in absolute value, so in magnitude, and we know that this is upper bounded by the integral of the product of the absolute values. And in turn, because we have just said that x is bounded by b, this can be further upper bounded by b times the integral between minus infinity and infinity of the magnitude of h of tau d tau. And we want all of this to be bounded, so we want this to be less than infinity. We want this to be finite. So we can deduce that for LTI systems, stability is equivalent to having the integral of h of t in magnitude dt finite, right? So that means that the impulse response h of t has to be absolutely integrable. So for a system that is stable, the impulse response h of t has to be absolutely integrable. So this is a way for us to assess whether a system is stable or not. In this slide we see a simple picture that gives us some intuition behind what we mean by stable or unstable system. So we have a pendulum on top. In that case, imagine that x of t is corresponds to pulling away a certain ball of the rest position, okay? You do that, and then the pendulum will start oscillating, but the system is stable. The oscillations will be bounded if x of t, the force that you apply, is bounded. On the other hand, if you look at the bottom figure, now the pendulum is placed upside down. And what may happen is that you apply a bounded force, x of t, small and limited, but the effect that this causes in terms of displacement, in terms of y of t, is unbounded, because the system is inherently unstable. So that's all for this class on continuous time systems. In the next class, we will introduce the Fourier representation of signals, starting with periodic signals, which can be represented with a so-called Fourier series. See you in the next class.